Module objectives. By the end of this module, you will be able to define metacenter and metacentric height, describe stable equilibrium, unstable equilibrium, and neutral equilibrium, and explain the analytical method for calculating the metacentric height. What is metacenter and metacentric height? Let's learn about metacenter and metacentric height. Metacenter is defined as the point about which a body starts oscillating when the body is tilted by a small angle. It may also be defined as the point at which the line of action of the force of buoyancy will meet the normal axis of the body when the body is given a small angular displacement. The distance between the metacenter of a floating body and the center of gravity of the body is called the metacentric height. Menu. This module has been divided into two sections: floating body and calculating the metacentric height. Click each section to explore more. Analysis of the forces on a floating body. Consider a floating body and let's analyze the forces acting on it. The first force acting on the floating body is the weight of the body, that is W, which is acting in the vertically downward direction through the center of gravity of the body, that is G. The second force is the buoyancy force, that is FB, which is acting in the vertically upward direction through the centroid of the immersed portion of the body, that is B, and is equal to the weight of the displaced volume of the body. For the body to be in equilibrium, FB is equal to W, since both the forces are acting along the same vertical line. Consider a body floating in a liquid as shown in the image. The body is in equilibrium and G is the center of gravity. B is the center of buoyancy. For equilibrium, both the points lie on the normal axis, which is vertical. The body is given a small angular displacement in the clockwise direction, as shown in the image. We can see that the volume displaced is larger on the right side, and therefore the center of buoyancy will now be shifted towards the right from the normal axis. Let it be at B' as shown in the image. The line of action of the force of buoyancy in this new position will intersect the normal axis of the body at some point, say M. This point M is called the metacenter and the length mg is called the metacentric height. Stability of a floating body. We learned about metacenter and metacentric height. Let's learn how to determine the stability of a floating body. The stability of a floating body is determined from the position of the metacenter, that is M. In the case of a floating body, the weight of the body is equal to the weight of the liquid displaced. A floating body can have three states of equilibrium, such as stable, unstable, and neutral. Click each state to learn more. Stable equilibrium. Let's learn about the stable equilibrium state. If the point M is above G, the floating body will be in stable equilibrium, as shown in the image. If a slight angular displacement is given to the floating body in the clockwise direction, the center of buoyancy shifts from B to B', such that the vertical line through B' cuts at M. Then the buoyant force Fb through B' and weight W through G constitute a couple acting in the anti-clockwise direction and thereby bringing the floating body in the original position. Unstable equilibrium. Let's learn about the unstable equilibrium state. If the point M is below G, the floating body will be in unstable equilibrium as shown in the image. The disturbing couple is acting in the clockwise direction. The couple due to the buoyant force Fb and W is also acting in the clockwise direction, thereby overturning the floating body. Neutral equilibrium. Let's learn about the neutral equilibrium state. If the point M is at the center of gravity of the body, the floating body will be in neutral equilibrium. G and M coincide, resulting in zero metacentric height. Weight of the body and buoyancy force act along the same line, resulting in zero torque. Analytical method for metacentric height. Let's learn the analytical method for determining the metacentric height. The image shows the position of a floating body in equilibrium, the location of the center of gravity and the center of buoyancy in this position is at G and B. The floating body is given a small angular displacement in the clockwise direction, as shown in the image. The new center of buoyancy is at B1. The vertical line through B1 cuts the normal axis at M. Hence, M is the metacenter and GM is the metacentric height. The angular displacement of the body in the clockwise direction causes the wedge-shaped prism BOB' on the right side of the axis to go inside the water, while the identical wedge-shaped prism represented by AOA' emerges out of the water on the left of the axis. These wedges represent a gain in the buoyant force on the right side and a corresponding loss of buoyant force on the left side. The gain is represented by a vertical force DFB acting through the centroid position of the prism BOB', while the loss is represented by an equal and opposite force DFB acting vertically downward through the centroid of AOA'. The couple due to these buoyant forces DFB tends to rotate the body in the counterclockwise direction. In addition, the movement caused by the displacement of the center of buoyancy from B to B1 is also in the counterclockwise direction. Therefore, these two couples must be equal. Couple due to wedges. Let's learn about couple due to wedges. Towards the right of the axis, consider a small strip of thickness dx at a distance x from y' as shown in the image. The height of strip x into angle BOB' is equal to x into theta. This is because angle BOB' is equal to angle AOA', which is equal to BM/B1, which again is equal to theta. Therefore, the area of strip is equal to height into thickness, which is equal to x into theta into dx. If L is the length of the floating body, then the volume of strip is equal to area into L, which is equal to x into theta into L into dx. Therefore, the weight of strip is equal to rho into G into volume, which is equal to rho into G into x into theta into L into dx. Similarly, if a small strip of thickness dx at a distance x from y' towards the left of the axis is considered, the weight of the strip will be equal to rho into G into x into theta into L into dx. The two weights are acting in the opposite direction and hence constitute a couple. The moment of this couple is equal to weight of each strip into distance between these two weights. This is equal to rho into g into x into theta into L into dx the whole multiplied by x plus x. This in turn is equal to rho into g into x into theta into L into dx into 2 into x, which is equal to 2 into rho into g into x squared into theta into L into dx. Therefore, the moment of the couple for the whole wedge is equal to integral of 2 into rho into g into x squared into theta into L into dx. The moment of couple due to shifting of center of buoyancy from B to B1 is equal to FB into BB1. This is equal to FB into BM into theta. This is because BB1 is equal to BM into theta if theta is very small. The moment of couple due to shifting of center of buoyancy from B to B1 in turn is equal to W into BM into theta. This is because FB is equal to W. However, these two couples are the same. Hence, equating the equations, we get W into BM into theta is equal to integral of 2 into rho into g into x squared into theta into L into dx. W into BM into theta is equal to 2 into rho into g into theta into integral of x squared into L into dx. W into BM is equal to 2 into rho into g into integral of x squared into L into dx. Now, LDX elemental area on the waterline is shown in the image. W into BM is equal to 2 into rho into g into integral of x squared into dA. However, from the image it is clear that 2 into integral of x squared into dA is the second moment of area of the plane of the body on the water surface about the axis y dash y. Therefore, W into BM is equal to rho into g into I, where I is equal to 2 into integral of x squared into dA. BM is equal to rho into g into I divided by W. W is the weight of the body. W is also the weight of the fluid displaced by the body. W is equal to rho into g into volume of the fluid displaced by the body. W is equal to rho into g into volume of the body submerged in water. W is equal to rho into g into V. Bm is equal to rho into g into I divided by rho into g into V. This is equal to I by V. Gm is equal to Bm minus Bg. This is equal to I by V minus Bg. Therefore, the metacentric height is equal to Gm, which is equal to I by V minus Bg. Well done! You have completed this module and your progress has been recorded. You are most welcome to revisit the module anytime to refresh your learning. Please take the post